write interactive coding and how it is not possible.
Thanks. This is John Krog with the Alkali. So this talk is about coding theory, and I'm going to summarize 100 years of coding theory in one slide. So in coding theory, Alice wants to send one message to Bob, M, but there is noise. So Bob doesn't get M, he gets M1. That's coding theory. We're dealing with this scenario. So actually, what I'm going to talk about is not this case, but the interactive case. So now, it's not the case that Alice has one message to send to Bob, but rather they have a conversation. They send messages to each other, and they want to compute some function of the inputs. And here we have two parties, but actually I'm going to talk about the multi-party case. We have not just Alice and Bob, we have many parties. So here are three parties, each one of them gets his own input, and they want to compute some function by sending messages to each other. The topology can be arbitrary, so we can describe it as a graph. Each node would be a party, each edge would be a communication link, so any neighboring parties can send messages to each other, and they want to compute the function. Okay, so it's very difficult to draw all these graphs with multiple parties, so usually when I'm going to draw a computation, I'm just going to use Alice and Bob, but bear in mind there are many parties, not just Alice and Bob. Okay, so the parties have this conversation, they send messages, they want to have this computation, but as before, we have noise on the channel. In this talk, the noise can be the BSC channel, the binary symmetric, the one that flips bits with some constant probability, each bit independently, or an erasure channel that just takes the bits and erases them. And the question, what happens now? How can they still compute the function despite the noise over the channels? Okay, so what we would like to do, like in the standard coding theory case, we would like to take a conversation and code it, add error correction, and get this new conversation that even if some of the messages were noisy, we would still be able to retrieve the original conversation. Okay, so this would be M, this would be M prime, but after decoding, we would still be able to get M. And one thing that we care when we do coding is a parameter called the rate. So if the original conversation took R messages or R bound of messages or R bits, and the new conversation takes capital R bits, then the rate is R over capital R. We want this number to be as close to 1 as possible, because that would mean that we didn't add much redundancy to cope with errors. Okay, so this is coding in interactive in the interactive setting. There has been quite a lot of work on the two-party case. Recently, there have been some work in the multi-party case. I'm not going to go over all this work, but let me just focus on one work in the multi-party case. It's a work by Rajagopalan and Shulman from 1994. And they show the following. They show how to code a multi-party interactive communication. And they said that no matter what topology we are talking about, let's assume that the graph has a maximal degree of D, then if somebody gives you a protocol that takes T rounds and has no errors, then we can take this computation and convert it into a resilient computation that will take T log T plus 1 rounds and succeed with high probability. Okay, so we took T rounds and made it T log D plus 1 rounds. This means that the rate behaves something like 1 over log D, so that if D is, again, is the maximal degree of the graph, so if everybody is connected to everybody, D is n, and we have a rate of 1 over log n. This is the worst case. This is really a bad rate or very low rate. But if the graph has constant degree, then the rate can be good, can be constant, not going to 0. So one thing to say about the result of Rajagopalan and Shulman, I need to explain the communication model that they use. And they use what we call a synchronous model or fully utilized synchronous model. This means that the computation works by rounds, and that every round everybody sends one message to all its neighbors. Okay? This is very common. So, for instance, yesterday we had the talk by Sylvia about the Byzantine agreement. That's exactly the model that he was using. There were rounds, and every round everybody was sending bits to each other. And this case kind of connects the round complexity and the communication complexity, because every round everybody talks, so every round just means 2 times the number of edge symbols, so the communication complexity and the round complexity is related by a fixed constant. So now bounding the round complexity means bounding the communication complexity. Okay, so this is the model, and many works followed using this model because it's very natural. But what we would like to ask is, why is this model justified? Why do we force everybody to speak at every round? So if I have nothing to say, why do I need to send you a message? Right? And we find something that we call, we don't have a good name for it, so we just call it semi-synchronous model. And it says that we still work by rounds, but now I don't have to send you a message. I can send you a message if I want to, which makes much more sense. One thing that we do ask is that the order of speaking is fixed. So if I want to send you, okay, we actually know in advance which party talks at which round. And this is actually quite critical. Changing this assumption kind of changes the model and changes the bounds that we get. Okay, so what are our main result? Our main result is the following. We show a communication lower bound of log n when our topology is the cycle graph. Okay? Formally, so if we have a cycle network and you give me some protocol that communicates t bits, now we don't have rounds. I mean, I don't care how many rounds, I care how many bits, because maybe in one round only one party speaks. If you give me a protocol with t bits, then no matter how you code it, it will take you t log n bits to code it in a good way. And this is a bit surprising. Why is it surprising? It's surprising because we're using the cycle graph. The cycle graph has degree 2. Each party is connected to 2 parties, one before him, one next to him. So the Rajagopal and Schumann says that you can have coding with a constant rate, not 1 over log n like we get. So this is a bit surprising. So let me explain why, like the intuition why it actually makes sense. So think about the following task that works over the cycle, and we have 1 bit of information that progresses along the cycle. So in the first round, P1 speaks with P2, he gives him the bit, then P2 makes some computation and gives the information to P3, and then on the next round, P3 talks with P4, the information goes along the cycle. This is what happens. If you think about the fully utilized protocol, what happens is that on the first round, everybody speaks with everybody. Although the relevant information goes only from P1 to P2. On the second round, still everybody talks with everybody. On the third round, everybody talks with everybody. Now, they talk, although the real information goes step by step, the fact that everybody speaks is very helpful for correcting errors. Because although I have nothing to say, I can still send some redundancy that will help me to correct errors that happen in previous rounds. Okay? So this in the fully utilized coding, we actually increased the communication by order of n, because instead of sending 1 bit in a round, we send n bits. And this is critical. This is critical for the error correction, but this forces an inherent blow-up of order of n bits. The thing is that this blow-up exists both in the original protocol and in the coding scheme, so therefore it cancels out in the rate. So we don't see it So this is why the Radjab-Koppelman-Schulman gets a rate of order of 1. If we think about it in a different way, it's just because this link of communication complexity and round complexity, because we force these two, actually what Radjab-Koppelman and Schulman did is giving bounds on the round complexity, and we just forced everybody to speak on every round, so we actually had some bound on the communication complexity. But if we really count the communication, we really count the bits that we need to send, we will see that we must have a blow-up of log n. That's kind of our observation. Okay, I'm not going to get too deep to the techniques. For some reason, proving lower bounds is difficult. I don't know why. Maybe it is. We use some information theory techniques developed not so long ago for the fully utilized model over star graphs. But apparently these tools are quite strong. We can use them for different models. And we do practically what I showed you. So we have the cycle task where the information progresses along the cycle step by step, and we just show that you must communicate log n bits in order to make the information go correctly along the cycle. One point here, we use large alphabet. This is actually make things easier. You can still show it with binary alphabet over the star, not over the cycle. But the same lower bound holds for any alphabet. Almost the same bound. Okay, let me summarize. So we show lower bound, communication complexity lower bound of log n in the semi-synchronous model over cycle graphs, where if you're not in a semi-synchronous, you assume that everybody speaks, you have upper bound of order of 1. We also show that this log n lower bound is tight. We actually give a coding scheme that has a rate of 1 over log n over the same graph or for the same task. So this log n is actually tight. There are several open questions. One of them is to extend the result to a stronger type of noise. So we only care about noise that can flip bits. But what happens if the noise can just take message and make it go away? I send you a message and you receive nothing. You don't even know that I send you a message. This actually makes things really, really difficult and very interesting. Another question is what happens with binary alphabet for the cycle graph. So for the cycle graph, we use a large alphabet. It actually was critical. We needed it in order to make dependency between all the parties. Otherwise, you depend only on the party before you. And if it sends you 1 bit, you can actually guess this bit with high probability. Half is quite high. So for our binary alphabet, we use the star topology, not the cycle. So the question is, can you show the same result with binary alphabet over the cycle graph? Thank you. Any questions?
What about avoiding the fixed order of speaking, but with bit flips without going to insertion definitions?
So if you allow changing the order of speaking, you need to make sure that this won't give you a lot of power to avoid noise anyway. So there is a way to encode information just by the path that you send the message to. If I want to send 0, I will send the message directly to you. If I want to send you 1, I will send it first to Elad, and he will send you a message, and you know that I sent you a 1 because you got it from Elad and not from me.
Okay, but I mean, still, it's a good communication complexity. Maybe I care just about communication complexity overall.
Right, but what I've just described a way that avoids noise. No matter what the noise is, I am able to code things properly. I think I didn't multiply the rate by more than 2.
But that's fine, right? That's one reasonable way to avoid noise.
Yeah, okay, so I'm just saying that this trivializes the model. It makes the solutions very simple.
So, but you... Okay, but then can you actually get like a full solution that gets like a reasonable? Yeah. Okay.
I have a question about the number of fronts. Is it implicitly assumed that the number of front T is like big enough? I mean, with regard to the original result, the KS 94, like if T is like log n, the probability of success is.
So we assume that T is very, very large. T goes to infinity. T is the parameter that we.
Is it an interesting regime for like if T is log n or something like that?
I guess that this makes things easier. Maybe then, even if you take each message independently and encode it independently, it will work with high probability. Thank you.